First, I think this is a slight detour from the file system. It's something I want to talk about, though. And then it has some relationships to file system, or really it has a relationship, I guess, to disk hardware. So here's how the MMU is working in conjunction with the OS in order to support paging. So the CPU checks the TLB. And maybe we can think of that as a separate MMU, but normally it's integrated with the CPU. So the TLB is a translational excite buffer, right? The TLB maps in our case, let's see, it'll be the PDX and PTX, right? That's the top 20 bits of an address. And it maps these to a physical page number. Okay? So 20 bits here goes to 20 bits here. So all of the addresses within a given page share the same TLB entry. Okay? TLB is very fast, but it's of limited size, kind of because of the fact that it's fast. So if the page table entry is in the TLB, right? And actually, there's a little more information. We get PDX, and PDX goes to the physical page number, and what else do we want to know? We really want to know the entire page table entry. So it really maps to, let's just not just say this, it maps to the entire page table entry, which includes as part of it the 20-bit physical page number, right? What else is in there that we need to know? Permissions, right. So basically, we're about to do maybe reading or writing. We may be in user mode or kernel mode. We need to be checking those permissions. All right? So those are in here as well. So if it's in the TLB, that's great. We go ahead and generate a physical address, do our checking to make sure it's valid. We're on our way. If we're not in the TLB, and so what's our cost, actually? So let's say the cost to access memory, ignoring caches here, is 100, what would be a reasonable unit? Seconds would be too big. Yeah, nanoseconds sounds good. So let's say 100 nanoseconds. And let's say the cost to access the TLB is something much less than that. Let's say, I don't know, 5 nanoseconds. So what's the cost then to access this memory? 105, exactly. Okay, nothing difficult there. Okay, now, let's say it's not in the TLB. Then we're going to access the page table. And of course, on the x86, it's a 2-level page table. If it's there, that's great. We have our new page table entry. We update the TLB, and we generate our physical address. What's our cost on an x86, then, for accessing this memory here? It's clearly got to be more than 105 nanoseconds. We got 5 nanoseconds here. In fact, let's just write it in, right? 5 nanoseconds here. We have 100 nanoseconds here to actually, once you got the address, get the memory. And accessing the page table costs how much? 200 nanoseconds, because we've got a 2-level page table. So our cost there is 305 nanoseconds. Clearly, the TLB is necessary, and it better be really good. It better have a high hit rate, right? Because this cost of 300 nanoseconds versus the raw memory cost of 100 nanoseconds might make you say, well, let's not use paging anymore, right? Let's not use virtual addressing. All right, and I forgot to actually say what if the page, so when we access the page table, was it in main memory? I assume, yes, it was in main memory. We went on our way. If it's not in memory, okay, we get a page fault, and we would go into the operating system. So here's where we would basically be all the operating system. Right? So we get a page fault. Do we have a free page frame? Is there somewhere that we can allocate this? So we're going to, the best example might be, let's say we were demand paging in code from our giant application, right? And so we execute some code we haven't executed before. That particular page in memory isn't there yet because we haven't loaded it. And so we want to load it. Where are we going to load it to? We need some free physical page to do that in. If we have a free physical page, great. We go ahead and start the read from disk. This is going to be an extremely slow process. And so it's going to then cause another process to run until it's finished. But in any case, we're going to tell it to read. We'll wait for the reading to happen. Once the reading is finished, we can go update the page table and then go back and try again. Right? And then if we don't have a free page frame, we've got to actually free one up. So we've got page frames. Some of them are dirty. Let's do an example. Let's just still say we're doing demand paging for our code. Some of the code we haven't used recently. And so therefore, we can evict that page. So that we're going to replace a page that's in memory with another page. So we'll go ahead and if the frame that we pick, our victim, is not dirty, then we are going to update the page table. And then go back and read into that now free frame. If it is dirty, before we use it, we've got to write it out to disk. Right? And then go back again.
Something's dirty, so it's been read before?
Dirty means it's been written since it was last saved.
Okay.
And the nice thing is there is a dirty bit in the page table entry that the hardware will do for us. So if we actually execute a write, it'll update that dirty bit. Does that make sense? Yeah.
So would you have another 5 nanoseconds like in the update TLB box, or?
I have no idea how costly that will be. That's a good question. So that's a good question. And the other thing we actually could do, instead of being 305 nanoseconds, it could be 300 nanoseconds. If instead of actually waiting to see whether the TLB has it or not, we go ahead and in parallel start going to the page table. And then we can just abort it, assuming we find it in the TLB. Questions on this? Kind of high-level concept of how this is all going.
I have a question not on this, but just on general, like threads and processes.
Okay, let's. Let me get just a page. Let's see. Oh, plus page. Ready.
So I know that the process has a lot more overhead than the thread in terms of like running it, but in terms of computer resources, it takes up the same amount, right?
When you say the compute resources, what do you mean?
It takes a core to run a thread.
Yeah, it takes when you're actually running, there's no difference between a thread and a process. Just if you have kernel threads, the kernel threads are slightly lighter weight than the process. Because if you look at it, let's say a process, we've got to keep not only registers, including the stack, we've got to keep a page directory, right, page table. And when we switch between them, we've got to switch not only registers, but also switch the page directory. And that is expensive. Why is that expensive to switch the page directory?
You have to invalidate all the TLD.
Yeah, you kill the TLD, you're back to 305 nanoseconds until you populate it again. So flushing the TLB is expensive. Okay. Indirectly, because filling the TLB is expensive is really the way to look at it.
Kind of branching off of that, so if you're switching between threads, conceptually, what would change? Does it be directory meaning?
For the threads, right? If you have multiple threads within a single process, switching between those threads is cheap because all you're doing is exchanging the registers, and you can leave the page directory, which means you can keep the TLB cache happy. Brad?
In the diagram, it says if it's not in the main memory, it goes into the OS. But if it's dirty, then it says it's transferred from main memory to disk. So it's basically saying that it's in main memory, but it's over here.
So here's the deal. Is this page in main memory? No. What we're going to do is we want to associate this page with a particular physical frame. Okay? And so we're going to find an existing physical frame that we want to use. So that's our victim. Okay? And then that victim we may have to write out to disk. That one is in memory. Okay? And then once it's written out to disk, we say, okay, now we're going to repurpose it for our use. We're going to update its page table entry to say that it no longer maps there, and update this one to say that it does. Okay? So basically, a diagram would be something like, we have physical memory, and we have our VM, and we have this particular virtual memory referring to this particular physical memory. And now we have this guy, so this is A, and this is B, and B doesn't point anywhere. And we got our page fault, and we say, oh, we want B to point to, some part of our code, let's say. So we're going to go through and we're going to say, okay, which of these do we want to get rid of? We're going to get rid of this guy. And so what we're going to do is check if it's dirty. If it is, write it out to disk. And then once we've written it out to disk, kill this, and then read from disk the stuff we want for B, and then set this over here. Does that make sense?
What happens if it gets written to while it's being written out to disk?
If it gets written to while it's being written out to disk, so it's a good idea. Let's change the order. So instead of writing first and then breaking this, break this and then write.
Okay.
Yeah, very good point. Is there another question? Okay.
What exactly are you reading out? Like, when you're saying reading out from disk for B, what is that? What is that exactly?
There's some simple possibilities. So one simple possibility is I've got my code for Excel, and I'm having to read this. I'm executing a function that causes me to go to this page. I've never been there before. And so I didn't read it in all ahead of time, because I know I don't need all that functionality of Excel most of the time. And so therefore, I'm demand paging it in. That is, as I execute stuff, it gets pulled in from disk into my memory, the code does. And so it's that piece of code. Okay. Okay. All right, a little bit about hardware and just some naming. So we've got a hard disk, which is spinning metal, right? The spinning metal has these heads that float on these platters here. So each one of these is a platter, and a disk head basically consists of a sequence of heads, one on top of each other, one for every platter. We spin around. The platter is broken up into tracks that are concentric circles. Actually, just one thing to note about here. Are we saving the same amount of data on each track? Probably not, right? Because we've got more stuff here. We got more magnetic bits in the outer cylinder than we do on the inner cylinder, so we can make shorter sectors here and still keep the same amount of data. So we got these multiple sectors. We have one of these tracks for every platter. So if you lined up, let's say, the outer track on the multiple platters, what kind of a geometric shape do you end up with? A cylinder. So that's in fact what this is called. We're called cylinders. So cylinders are a circular cut through the platter. moving parts are slow, right? That's the way we like just electronics, but this is actual mechanics. And so we've got a lot of time. We've got the time that it takes for the drive to spin around until we get to the sector we want. On average, how long will that be? How many revolutions? Say again? One was our worst case, right? Our worst case is we just missed that sector. So half is our standard. So when you look at seek time, when you look at rotational time, you just have to, on average, pay half. Now, if you're reading a bunch of sectors that are on the same track in order, the disk drive can read them one after another, after another, after another, after another. So it's really nice and quick to be reading a batch of adjacent sectors. And we can also actually be reading not just this sector, let's say, but we can read all of the sectors in the cylinder at the same time. So these disk heads will all be reading in parallel.
So it's able to, like, it's fast enough to pick up a read along the same location and not have to wait for the sector to come back to.
It is fast enough to do that in some circumstances, and I'm not sure whether that's true of hard drives today, but I think in the past, if it wasn't fast enough to finish this sector and read the next sector, then the actual logical sector after this would skip one, so that whatever the distance needed to be, so that it could read one, read the next, read the next, read the next. Does that make sense? Okay.
What if your sectors are like lined up backwards? So like you want to, you know what I mean? Worst case.
Yeah, don't do that.
Is that like,
I mean,
is there anything that like forbids you from doing that?
I mean, you as the operating system get to decide what goes in each sector. A lot of times the hard drive hides from you much of this information. It used to be, in the past especially, you would carefully find out how many cylinders are there, how many platters are there, and so on, so that the operating system would very carefully lay stuff out. But a lot of that, as I say, is hidden now, and it kind of looks as though it's just from 0 to n-1 sectors. But it does lay them out, so that if you're going from 0 to 1 to 2 to 3 to 4, that should be relatively fast. So it's not going to say 0's here, and 1 is over here, and 2 is over here. Okay. And then we've also got the seek time. So we've got to actually move this disk head zzz in or zzz out. Right, that takes time too. And then we all actually got to transfer the data. Okay. We always read and write in here a sector at a time. Okay, so we're reading or writing the entire sector. The mapping, as I say, the hard drives normally are doing this mapping these days. You don't find out about cylinders, heads, sectors. Blocks go bad. Hard drives can fail. So we have error correcting codes, like we do on a CD-ROM, where each sector has additional bits for the errors. So what's the minimum number of bits you could provide for error detection? 1. How would you use that for error detection? So I say my sector has, I don't know, it's this big, and I'm going to give you 1 extra bit, and you can then determine if a cosmic array hits and changes it or something else. Yeah, Andika? Parity, sure. XOR. Yeah, that's very common. It's done in memory, not as much these days. It's very uncommon to find parity memory. But parity, this extra bit, will allow it to tell you some bit was swapped. Okay, now, if 2 bits get swapped, you're in trouble. You can't tell anymore. So if an odd number of bits get swapped, actually, you're fine. By adding more bits, we can actually not just detect errors, but correct some number of errors. So if we provide extra bits, we can say, not only did an error occur, but I can fix it. Okay? So those are called soft errors. Soft errors are fixable errors. So our error correction was necessary, but it worked. Okay? And our hard error is error correction was necessary, but it didn't work. By working and not working, what I mean is there were few enough errors that it could fix it, or there are too many errors, and all it could do is tell that it was a problem. So if you've got a hard error, that's a problem. You've lost. If you look at like audio CDs, you can get hard errors, but still you get the data out, and it's like, who cares that some of the bits were off? But if you've got a code, for example, it's probably almost guaranteed that even a single bit error will be bad. Does that make sense? The soft error, what might you do with the soft error information, knowing that you had a soft error? Start saving your pennies for a new hard drive is one possibility, right? You could not use that block anymore and decide that looks like, you know, I've gotten soft errors on that same sector so many times, I'm going to not use that sector anymore. Okay? And in fact, the hard drive itself will, I take it back. I don't know actually whether it does on the fly. What it certainly does is when initially a hard drive gets formatted, it figures out which sectors are bad and remaps them. So sector sparing is just sort of remap. Sector slipping is move, sort of slide sectors up. So if we have sector sparing, and we've got, let's say, 1, 2, 3, 4, 5 sectors, and 3 is bad, what we do is conceptually map that, let's say, to the last one. So we have logically 4 sectors. We have some extras in case something goes bad, and we will just point it to the new one. In sector slipping, we want to avoid this problem. I said when you go from adjacent sectors, it should be quick. This could be not quick, right? Because we're going from 3 to someplace later. This might not be 5, it might be 500. Sector slipping says, let's just conceptually move all these up. Down, down. So this would be 1, this would be 2. We'll then call this one 3 and this one 4. So we're reading or writing. What do? We seek. This is what the hard drive does. It waits for the sector to rotate, and then it reads or writes. When you're reading, you can't do anything but wait for the read to happen. And that's not even true, right? Hard drives have caches in them. They have buffers. And so when you issue a read, it'll actually first look in its buffer. And if it's got it in there, it'll give it back to you. If you're doing a write, it can just go to the buffer and return immediately, which is what it does. I talked about the fact, though, that you would be very unhappy if you had a power outage and stuff got lost. And so we do have hard drives that will use the rotational energy to, in a final gasp, write the data that was in the buffer. And so there's all this caching happening sort of at all levels of things, including in the hard drive itself. And unfortunately, sometimes there are errors there, and that's really unfortunate.
So I didn't quite get what the critical difference was between sparing and slipping. It seems like you kind of were doing the same operation.
So let's look. Let's say we have 1 to 100 here, and then we have some spares here. If 3 goes bad, then we're going to have a pointer from here to here. Now we can't store it in there because it's bad. So it's somewhere elsewhere on the drive. It's going to maintain the fact that 3 actually maps to 101. Okay?
So is this the operating system that's taking?
No. This is the hard drive taking. It could be the operating system. Often it's the hard drive that's doing this.
So like the hard drive has like some code on it that like handles detecting bad sectors on itself.
Yeah. Oh, especially when so for sure when it initially gets formatted. That's when you do a low-level format. It's part of what it's doing, checking and seeing which of the sector. So in the old days, you'd buy a hard drive, and on the top of it was a little label, and it said, these are the bad sectors. And then you would use your OS to do this thing for you. But nowadays, that's in the hard drive itself. But you know when you buy a hard drive and you get this rated capacity of, I don't know, 4 terabytes, but when you actually go format and everything, you have a lot less? Part of the reason is the 4 terabytes is very optimistic. It says, I've got all these blocks, including spare ones I'm never going to actually directly give you access to. So. The slipping says something different. The slipping says in the same situation, we would go ahead and renumber. So this is 1, 2, 3, 4 here. We would renumber. This is 1, 2, skip 1, 4, no, sorry, 3, 4. And then this last spare here, the first spare, would be 100. So going between any 2 of these is still cheap. Going from 1 to 2, 2 to 3, 3 to 4, because we only moved it down a little bit, as opposed to going jumping. Does that make sense?
Yeah.
Okay.
I mean, is there any reason you want to do sparing? It just seems sad.
Yeah, it seems worse, for sure.
Because then you don't have to move everything else.
That would be an advantage. You didn't have to move everything
Bad
else.
sector.
The other thing is you could just put the spares all in one place. To do this slipping, you have to make sure you have spares carefully, you know, at the right places to be able to move stuff down. So, all right, disk spaces. This is really not just disk specs, rather. This is just some I picked up a few years ago, but you can see rotational speed is different. Did you have a question?
Yeah, about when you were talking about the recovery strategy, where like the drive is using like the momentum and slow in it, does it have like sectors that it goes to dump the buffer into?
I have no idea. Yeah, that's a good question. Does it have enough energy to actually write all the stuff in the right places, or just to write it in a log that when it comes back up, it can fix it? Either one would work as long as the user of it couldn't tell. Right? Why do we want higher rotational speed?
Because it means there's less time, that it takes less time to go half all the way around to...
Yeah, that average rotational latency is lower. Plus, your transfer speed should be higher because you're going to be touching more sectors per given unit of time, right? You'll be passing over them. So the average rotational latency is exactly related to the RPMs.
Why does that not improve more? Like, I would expect it to get cut in half, almost.
We maybe just have some rounding here. You know, this may be 2.9 and 4.5 or something, but we could easily compute this and see what the actual numbers are. The access time. So the access time, why is this one so big?
It's probably a bigger hard drive, so seek time is bigger. Like, I'm
Yeah,
guessing
exactly.
2.5 versus 3.5.
This is a 1 versus 4 terabyte, right?
I mean, that would make a difference. But if it's like a 3.5 inch drive...
Oh, I see what you mean.
3.5 inch
Yeah.
drive, it's just bigger platter, so it takes longer to go across.
This could very well be a larger drive. And so there's more seeking that happens. But that's where the difference is, the seeking. Average transfer rate is higher, partially because probably got this higher rotational speed. And
you have a higher rotational speed, but at the same time, a quarter the data density wouldn't...
Then that would not be as... Yeah. We couldn't have a side transfer speed if we also reduce our...
But it did reduce in capacity.
Well, we reduced the capacity. We also said the size was different.
Fair.
We don't know how many tracks there are.
Okay, that's valid.
So, all right, so we issue, so we're in our operating system, right? And we have got some requests from different processes to read and write blocks, okay? Those can be explicit through like read or write system calls, or those can also be implicit. Give me another system call that'll cause a read or a write. sorry, not a system call. Give me something a user program could do that caused a read or write.
Create a directory.
Okay, create a directory for sure, and we'll see some examples of that today. What about if I just have a instruction in my code that says A equals star B? Could that cause a read or write to disk? It could cause both, right? If I'm indirecting in a pointer, that means I need to go to that address. And if that is not paged in, then that may cause a write to write a dirty frame to disk and a read to read in from disk, that page that has been swapped out earlier. So anything at any point could cause possibly a read write. So we got all these read and writes, right? Requests. We've got read 3 and write 5 and write 1 and read 7, let's say. All these, and they came in this order. In what order do we want to issue them? Well, one possibility, FCFS, which stands for?
First come, first serve.
First come, first serve. So that would say, do them in the order they came in. The problem is, if you have some unfortunate situation, you might be bouncing back and forth between low block numbers and high block numbers, which is causing seek, seek, seek. Okay? Well, you can actually hear, by the way, if you hear a hard drive that's doing a bunch of seeking. Yeah. Another possibility, and much of this has been subsumed in the hard drive controller on the hard drive. So the hard drive gets these requests, and it will actually reorder them. So shortest seek time first. Go where it's closest. Okay, this might be considered a greedy algorithm, right? This can be a problem if you've got, I'm going to look at it linearly. Okay, so we've got low block numbers and high block numbers. And let's say we have a request here, and we have a bunch of requests that are continuing in this range. Okay, so the head is in the middle here, and we've got a bunch of requests that keep coming in, and the shortest one is always in here. What about this poor guy? He doesn't get to go until there aren't any close ones. Okay, so that can be difficult. The elevator approach says start at this end and go up, and just keep always going up. Satisfying requests as you go. And then when you get up to here, go back down, satisfying requests as you go. And go back up and go back down. Is that fair to all of these sectors? No. I would much rather be in here than out here. Okay? If I'm over towards the edge, then as I come up here, there's unlikely to be, as I'm going from floor 99 to floor 100 and then back to floor 99, there's probably no new request for floor 99. And then I've got to wait from 99 and 98 all the way back down to 1, ignoring this is low and high, and then all the way back from 1 to 99. So I've got to wait probably 198 steps before we come back to here. Whereas if I'm in the middle on 50, I've got an average of 100. So I go from 50 to 100, 100 back to 50. 50 to 0, back up to 50. Okay? So it's preferentially treating the guys in the middle. A C-scan says it's circular. This has the counterintuitive property of you go from low to high, and you send your elevator up, and you just skip everybody. And only on your way down do you start satisfying requests and satisfying requests and satisfying requests. So then go all the way up, and then, so everyone is treated equally that way. True.
Can you repeat that again, the treated equally?
So the circular span is where we scan, is where we don't do anything when we're going up. And then service requests on the way down.
How would that be implemented for something like on a hard drive where you've got the cylinder and then also the track number, and essentially there's like 3 different axes there?
Well, we're caring about seek time mostly here, because that's really the most expensive part. And so we would satisfy everyone in a cylinder, probably.
Okay.
And then go on. And so what we'd be talking about here is entire cylinders. Treat them all the same. Okay. And then solid state drives, which are more and more common, right? We have flash memory. The access time is much, much quicker. Internally, they're really complex, and the transfer time can also be much higher. They're really complex for a couple reasons. You have to erase before you write. There's a limit to how many times any given block can be written. And so therefore, the SSD has to do this remapping of blocks, okay, which can be expensive. And what's worse is a lot of the logic on them, at least historically, has not been good. It's like SSDs that just don't work right. So working right is a nice thing for your permanent storage. I suppose it's not working right.
So when you say this limit, how many times? Is that like how many times ever? So you can only write so much, and then
Per block.
It can be erased.
Yeah.
And then basically whatever's written there is stuck there, and it can't be rewritten.
Yeah. It's on the, so I'm trying to remember some old numbers. There used to be problems. Yeah, it's around 10,000 is about the number. Thank you. So, which doesn't sound like that much.
But
Yeah.
SSDs will have a bunch of spare blocks
Yeah.
that they don't allocate initially and are used to remap sectors that can't be erased.
Kind of sounds similar to
In
what we're talking
practice,
about.
the life of an SSD will be similar to the life of a mechanical hard drive if you're writing it at a relatively high
They
rate.
usually advertise the size conservatively.
That's the
Yeah.
case.
So,
On the cartridge.
okay, disk blocks. We normally, a sector commonly might be 512K. We might commonly group together multiple sectors into larger blocks, and the OS would deal with blocks, like let's say 4K instead of 512K. And this just makes life easier. You reduce your overhead because you're just dealing with fewer blocks than you would be sectors. We know that they're contiguous, and so quick to access a block. And so seek time will be reduced. XV6 just uses single sectors, okay, just to make life easier. So as we're looking at that code.
So sector is always 512K.
No.
So
No.
block-
I'm sorry. Why am I saying K here? 512, right? Bytes. Half a K. It's common. It's a common sector size.
Okay.
Yeah.
But both sector size and blocks are kind of arbitrarily defined by numbers.
The manufacturer defines a sector. The operating system imposes a block size.
Oh, I see.
So
That are usually multiples of a sector. Right?
always would be, it would just be crazy not to make a multiples of a sector. And of course, these are all going to be powers of 2 because people are rational for the most part. We talked a little bit about the file system API. In fact, there's not a lot I want to talk about here. But I do want to talk about this, file descriptors. So when you have a file descriptor open, you're guaranteed while you have that file descriptor open, you can read and write to that file. Assuming you have write permission, you can write to the file. What if someone removes the file? Doesn't change the guarantee. The guarantee is while you have a file descriptor, you can read and write to the file. Okay? What that means is, if someone renames it, well, you still have a reference to it, and so you can still read and write to it, and it'll be read and writing to that new thing. We talked about the links. So for hard links, we can have multiple links to the same file data, and so therefore we must have some reference, and we must have some reference count. There are 2 reference counts we have. There's a reference count of how many links we have to a file, or the content, and then we also have how many file descriptors are open. The number of links, so this must be on the hard drive. Okay? The open file descriptors is usually just in memory. well, is just in memory. We need this one because when we shut down our computer and then start it up again, we still have the same number of open links. But our open file descriptors just has to do with our running OS with the processes that are there, and that stuff is all going to be kept in memory. So we'll have a copy of this inode in memory where we'll also keep track of how many open file descriptors we have. And only when all of them go to 0, both the number of links and the open file descriptors, can we actually delete it. Yeah.
Why do we need to keep track of 2 separate numbers as opposed to just knowing the sum of them?
Then we'd have to be writing onto the hard drive every time we did an open of a file.
Oh, that makes sense.
So, okay. We got our system calls. We got our file descriptor operations. Okay. We've got some name operations. So if we have open foo/bar/a.c, okay, our system call is going to actually have to be iterating through here. So starting at the current directory, and then going to this name, and finding its inode, and going to this one, and going to this one. So that's there. We have inodes, where our inodes are the reference to the actual data. We have a cache of those inodes because we want stuff to be fast. So if we're doing a lot of stuff in our current directory, we would like the inode for our current directory to be in memory so we don't have to keep hitting disk. We have an ID driver, which talks to the hard drive. Above that, we've got a buffer cache. If we are constantly working with a particular file, don't want to keep having to read and write it to disk. So we have a cache in memory that we deal with. And then we've also got a log, which deals with the fact that if we have an error, we want to be able to recover from that error. Okay, and we'll talk about that separately, not today. So looking at XV6. XV6 has 2 IDE drives. One contains the kernel in the boot sector, and the second is our file system. Okay? So what's on our file system? Like, what files are on our file system?
User program?
User programs. Hello, echo, cat, all those are on there. So that file system gets created as part of the make process. What's a file system look like? We've got a bunch of blocks. Block number 0 isn't used. The reason block number 0 isn't used is because sometimes this file system might be the boot drive, and the first block is usually the boot code, okay, which we have on our first ID hard drive. So this one's not used. Yeah.
What is an IDE disk drive as compared to an actual disk drive?
IDE is a controller, and it basically defines the bus, right? What are the wires that go, and what is the protocol for talking on that?
Okay, so it is literally 2 different pieces of hardware, these 2 IDE disk drives that we're talking to.
Not when we're using QEMU.
Okay.
When we're using QEMU, it's conceptual, but yes, these are really, we're assuming we installed, if we wanted to run this on real hardware, we'd have to install 2 hard drives.
Okay.
Yeah.
That's not usually what you do, though, right, with like modern operating systems.
No, it just makes life easier for now. And yeah. One is our super block. So our super block is going to keep some information about the rest of this. We'll talk about it in a moment. We have logs from 2 up to 31. So this is 2 all the way to 31. 32 to 57 are arrays of inodes. So each inode is, we'll see in a moment how big. So it's X bytes. And we pack these together. So if we have one block, then we have inode, 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 etc. Okay. We have a bitmap that tells which blocks are in use or not. Okay. And then of these next ones. And then from 59 on is right, infinity. I don't really mean infinity. it can't be any bigger than how many bits we have in this block, right? Because that tells us what's free and what's not free in here. Yes?
On the previous slide, you had mentioned that a block was an array of sectors, but now
Yes.
it seems that it's an array of inodes. So the
No. Well, here's what I'm saying. I'm saying these blocks, 32 to 57, are arrays of inodes. Okay. This one is, so that's these. The log has different definitions. The block here is a bunch of ones and zeros. Okay.
So where did the sectors come from, the array of sectors?
Each block is composed of some certain number of sectors that the operating system defines. XV6 is going to be 1 to 1. So this is actually sector 0, sector 1, sector 2, and so on for XV6. In other operating systems, this might be 0 to 7, 8 to 15, and so on. Okay. Make FS. So this is a program that actually runs on Knuth. So it's part of the make process, and it makes, I think it's called fs.image. So fs.image is this file that has the format I just showed you. So it has code to create a superblock and things like that. What's in a superblock? Superblock contains information like, basically it contains pointers to here and here, and I think here, just enough to find the beginnings of all the other stuff. Okay, because you might have a different file system layout that had more inodes, right? The number of inodes is just a constant when you're building the file system. Good question. Okay. Once you've built the file system, this meta information is static, this layout. The bitmap here, of course, is going to change. These content blocks are going to change. The inodes are going to be modified. Superblock, I believe, is not going to change. We'd have to look at the definition of that. Okay, I think that should be constant. Okay, so let's look at an inode. Inode, we have file type, like directory or regular file. Or we could have some sort of a device. So this is file, directory, device. If it's a device, what kind of device? Well, the major number tells us what kind of device. And the minor number tells us which of those devices it is. If you had USB ports, let's say, USB ports is a bad example. If we had, I'm going to just say serial ports, even though no one sees those anymore these days. Our major for all the serial ports might be 5. And the first serial port would be minor 0, the second one minor 1, the third one minor 2. So they'd be using the same device driver, the serial device driver, but then this minor number would tell you which one are you actually talking about. Okay? Actually, disk drives work similarly. How many links? So if it's 0, then it's not linked to anywhere. How big is the file in bytes? And then what are the data block addresses? And we talked about the fact that we have direct and indirect blocks. So in this case, we have 12 direct blocks. So that means we can support up to 6K file, all with direct blocks. And then we have 1 indirect block. So that'll give us another, we have to do the calculations, however many addresses we could fit in 5 of 12, so that's 128 more blocks. So a total of, looks like 140, I believe, blocks. Which is not that big, right? That's a 70K. So we're limited on our file size. If we've got byte 8000, right? We're in a file. We're doing a write at offset 8000. Which block is that going to be? Right? It's going to be 8000 divided by 512, which gives us
15?
Let's say 15. Okay, 15 seems like the right number because 8192 would be 16. Yes, so that's 15. Okay, and so that, well, plus this is useful too. So that means it's not in one of the first 12. So it's not in a direct. It's in the third entry in the indirect block. So if we want to get to it, we have to first go to adder at adder at 12, right, which is the 13th entry. Read that block, which we hope is in our cache, and then go to the third entry, so that's at offset 8, and read those 4 bytes, and that'll give us our new block number, and then we can go there. Okay, so basically what we had was 12 of these, and then one of these that goes over to here, and then that one takes us into here. And that says where in the block we are, and then we can figure out what byte we're at just by taking 8000 mod 512. Make sense? Okay. Each inode has an inumber associated with it, similar to how each, I don't know, each page has a page number. It's just its entry in this large array. It's indexed in the large array. So we have 64 bytes. IPB is a constant that's declared, right? This is 512 divided by 64 equals 8. So if we want to find what block number the inode is in, well, we know the inodes start at 32. How do we know it's 32? The super block will tell us. So if someone just gives you an XV6 file system, you look at the super block and it'll tell you where the inodes start. Okay. So this is from the super block. And then take the inumber divided by 8, and that'll tell me how many blocks you have to go. That makes sense. It's simple. It should be simple. Oh, my goodness. Okay, directories. Directories are just files, except their type is different in the inode. It says it's a directory. And this is a directory entry. And basically, we've got not that. Right, so we've got our directory inode that points to these blocks, and this is one of the blocks, and it's going to have a bunch of directory entries. So this is directory entry 0, directory entry 1, and so on. And each directory entry is very simple. We've got, inum stands for inode number. And the only other thing we need to know is what's its name. We don't need to know permissions because we don't support permissions. We don't need to know who owns it because we don't support ownership, right? How long can a file name be?
Up to 14 bytes, or maybe 13?
Yes, so it's 13 or 14. So 13 makes sense because we need one for the null byte. But someone said, well, wait a second. If the last one's not null, and there's no null before that, then we would know it'd be 14 big. But when you're working with a directory, everyone who's working with directories has to have a special code to check whether it's, how long it is and put in so it's kind of a pain. But that is what was traditionally done and what is done in XV6. So it could be up to 14 big. And if it's 14, if length is 14, not null terminated. So how many directory entries in a block?
Which one's 16 bytes? So
512 divided by 16. So 2 to the 8 divided by 2 to the 4th, which is 2 to the 4th, which is 16. Right? So 16 per block. How many files can you have in a directory? What would determine that? 140, which is the max number of blocks, times our 16. Yes.
Wait, so can you explain that 16 per block again? 16 what?
14 for here. for the name, right? Plus 2 for this short. This is a 2-byte value, which is the I number.
So it's 16
Bytes,
per.
directory entry. Yep. So size of dirint, really it's size of struct dirint, is equal to 16.
And then
Wait, wouldn't that give you 13 per block? Oh, sorry, 32 per block?
13, I'm sure, is wrong. Okay, so 512 is 2 to the 9th divided by 16 equals 2 to the 4th. Yeah, so it equals 2 to the 5th equals 32. Yeah, so, yeah, good point. This makes sense? So if we have an I number, we basically we can get to the associated inode, and that gives us information about the contents of the file and the type of the file and how many links there are to the file. By the way, inum of 0 is special and means none. So inode 0 or inum 0 equals no inode. So how do you specify that you've got a directory entry that's nothing in it? Set the inum to 0. All right, we're going to look at disk writes, and we're going to look what happens to these on-disk data structures, to the various blocks, looking how it's updated. So here's what I did. What I did is over here. I removed file system of image, because when you do a make, it does not rebuild the file system image. The reason for that is if you ran xv6 and, echo hello into foo and quit and come back in to Kimu, then that'll still be there. And if you do a make, it'll still be there. So if you want to remove the file system, you've got to explicitly remove it. Okay? And it will be removed, I think, if you change the user programs. It'll realize you want that user program on your file system because you made it because you want to use it. And so then it will rebuild the file system and blow away what's there. But in any case, I remove file system, I make, and then I did an echo into A. And I set a breakpoint at, I think it's called log_write. We don't care about the logging part right now, but it's the thing that is eventually calls ID RW to do reading and writing to the ID disk. So what happens is, and then every time it stopped, I just did a backtrace. Okay? So what we find is the first one is it does an ialloc. I for inode. So it's allocating an inode, calling from create. That kind of makes sense. We're creating a file, we're going to need an inode for it. Except, so mark inode allocated. That would be basically our inode. We need to mark that it's no longer free. So we have, go back here. We have our inodes, and we need to know which of these are free and which are not free. We notice don't have a bitmap or anything else, so we must just iterate through here to figure it out. And let's see.
It's just echo statute.
Oh, yes, that's a very good point. So dinode is what describes, yeah, we had a slide on this, describes. So I believe this one sets. Let's look a second in create. Create is in syscall sysfile.c. All right, so we're allocating something of a particular type. That's where we're doing this. And this is the one that's going to do the write. So it's going to go through basically all the inodes. SB.inodes, what's SB stand for? Superblock. So the number of inodes is kept in this superblock. And we go through and then read each of the blocks. And we're going and trying to find one that's free, which means it has a type of 0. Now, we're not actually doing all this reading necessarily because our block cache is going to keep all this in memory. So many of these inodes blocks are going to be kept in memory because we're using them. So these are not going to cause a lot of disk access. But what we do want to do is mark this one as in use, and then log write is where we actually write it. So the first thing we've done is set its type and written it. And that's block number 34. Does that seem reasonable? 34 is in the range of inode blocks. What's the first inode block? 32. So what happened to 32 and 33? Why didn't it find an empty one? In use for what, though?
User programs.
All those user programs, right, that MKFS created. So Echo and CAT and all those all took inodes, and so they're all in use. So we have spilled over into the third block of inodes. Now what happens? Now I update, again called by create, initializes the number of links. So the number of links will be 1. Major, minor, those other things, let's just see. Yeah, I think major and minor aren't relevant given that this is going to be a file, right? Because I'm doing echo greater than A. So we'll update the, in our case, what's most important is the number of links. And then we need to actually write in the directory, right? We need to write in what directory? Are we going to create this file named A? Slash?
Like the home directory?
Not even the home directory.
The current directory?
The current, yeah. It's like whatever the current directory is. Who stores where the current directory is?
The shell and possibly also the kernel?
The shell doesn't. The kernel does. Because if you think of it, this is a kernel call that's saying create A. And so it has to know what current directory is. And so where is it just a single global in the kernel?
It's
Per
process.
Per process. So this is the current directory is per process. So if your file name starts with a slash, it's going to start up at the root inode and keep going through to find stuff. But if it is not start with a slash, then it's going to always start at the current directory. In our case, there's no components to the path, so it doesn't have any more directories defined. So it's going to be creating A in the current directory. And that is what this is going to be. So we are in directory link. We're going to be writing the I number and the name. And then that's it. Where's our data block for A? What's the data of A?
A single new one?
No. Gosh, that actually sounds reasonable, but it's not. I believe echo by its...
Yeah, echo by itself gives a single new one.
yeah. Yeah, our echo does.
QuickTab says like weird things, maybe echo.
Let's just see. No. No. It...
Looks like it would give it a single.
We're going to go through 0 times in the loop, right? So, yeah.
Okay.
So there's a special case of echo by itself. Thank goodness. All right. So what's going to be in the inode? And in fact, if we look at 30, what's in block 34? Block 34 contains so this is block 34, and somewhere in it is our inode, right? So we're going to have a type. What's our type going to be? File, device, directory, file. We're going to have a major and minor that we don't care about. We're going to have a number link, which is 1. And what else do we have in a inode? Andy?
Like the array of them.
Yeah, we have all our adders. What are all the adders going to be? Yes, so there's all going to be 0. Whereas 0 for our block number means it's nothing. Just like I number for 0 means nothing. So we don't have any adders, and what's the last thing we need? Feel free to look back on the previous slide where we defined the DI node. Where was it? There, DI node. So what's the one other thing is the size. What's the size going to be? So the size is 0. And that's really all we need to know about it, right? We don't need any data block. All we need to know is it's a 0-sized file. We already explained why this is 34, because there exist other files. And why are we writing twice to 34 here? Yeah, basically, once we've allocated the inode, if we don't mark it right away, then we have the potential of, let's see, a better example here too. So what goes wrong here? I will have to come back to this because I don't remember why it's important that we do it twice. But we are updating 2 different things. One, we're just marking it as no longer free, and then the next one we're marking things like the size. Yes?
I kind of thought when I was doing the homework that like the log write didn't actually cause it to be written. It was just marking it so that it was written when you released it. So isn't it just that you're marking it twice as dirty, and then it only actually gets written, you know, after you release it at the end? Or am I misunderstanding?
I am not sure about the interaction with the logging. Yeah, whether we end up with actually 1 disk write or 2 disk writes is a separate story from where we're writing. We're calling write once or twice. Block 59. So block 59 is this one we called. So that was our directory. Is this an inode we're writing into? Just look at the structure of our disk layout. Inodes go up to what? 50, I don't remember what the number is. Whatever the number is, 57. And then we have a bitmap, and then we've got 59 is our directory. Okay? So it's interesting. The very first data block happens to be the / directory. So what's in it? We got a bunch of stuff. Okay? If we do an ls, it's kind of handy because the ls for xv6 prints out inode numbers. So these are inumbers. Okay? And this is, I believe, the type, which kind of makes sense. We've got directories, and then we've got a bunch of files. The last one is A with inum 19. And so that's what's written in the directory. We have a 19, and we have A followed by \0, followed by more \0s. We see the dot and the dot dot that we talked about on Monday. The fact that this is the root directory. We can tell it's the root directory because dot and dot dot have the same I number.
What's the console?
The console is, that's a good point, it's a special file. So this is an actual device. And it's a device that does the reading and writing to the screen.
So it can be file, device, and then what was the other?
Directory.
Directory.
Yep. Questions? Yeah.
Sorry, the type refers to.
The type is in file, directory, device.
So
Okay.
how much size is
Size. Yep. Why is dot 512? None of the rest of these are powers of 2. Well, I guess console and A are power of 2, but none of these have to be powers of 2. Why is this size 512? Why isn't this, I don't know, something else? What does this mean?
Is that the block size?
It does happen to be the block size.
So is it just referring?
We've allocated one block for like directory.
Yeah, directory entries get allocated block at a time. So it allocates a block and it zeroes it out, right? And then if it zeroes it out, that means the I numbers are all 0. And then it goes ahead and starts using these directory entries, okay? And if it got if it got 128 of them, then it needed a new block. Sorry, not 128, however many fits in here. 32, is that what we decided fits in here? Yes, 32. So if you tried to create a 33rd element in the directory, it'd allocate another new block, zero it all out. This would now be 1024. Okay. So a directory will often have unused directory entries within it. And I don't believe in XV6 there's any freeing that takes place. So if you go through and now remove, let's say you spill over in a new block because you have 35 entries and now you delete 5 of them, even if the ones you deleted are here, it's still not going to release this block. It's an optimization one could do. If you remove echo, it's going to go to this entry, zero it out, do nothing else. If you're trying to create a directory entry, it goes from the beginning and iterates through until it finds one that's empty. And if it doesn't, allocates a new block for it.
Why isn't that similar logic for files? Like why are files like the sizes?
For files, we actually care about how many bytes are in it. Because when we allocate a file, some file systems you get blocks at a time and you have to kind of keep track of it. You know, like putting a special character at the end of your file. But in our case, it is handy for us to ensure the file system knows how big the file is. So that we can, for instance, ask it how big the file is. And so that's why we allow different sizes here.
So like with the files,
Like 2327 is a good one.
So like with the file store, they were like, I don't know, like what's after that? Like after there's 2,227
Oh.
bytes.
Bytes, more bytes,
That
0.
can also be mapped to like another file.
No. So that would be an example of internal fragmentation.
Right. Okay. So there's still okay.
Yeah. So if you try to write to those, you can write to those, and it won't have to allocate any new blocks until you get to a new block. Okay. What if more than one process calls ialloc? You wouldn't want them to return the same I number, right? And so what happens is bread sets a lock. Basically, it locks the block, and brelease frees it. Okay? So as you're iterating through, when you read a particular block, no other process can be looking at that same block at the same time, right? It will be wait here until this gets released, and then it will continue on. The other process will continue on. So this critical section can only be executing by one thread for a particular block at a time. Is it possible you had multiple threads both allocating inodes at different blocks? Yes. I can imagine one process going through and finding no free entries in the first few blocks and getting to a much later block that it's looking through. And then another process comes in and removes a file or something, and that frees up some inodes. And then another process comes in, and it's at the beginning of the for loop, and it's at an earlier block that this guy already went past because at the time there was nothing open there. But you can see if we did not have a block cache, it would be really expensive because we'd have to hit the hard drive for a number of inode blocks until we find an empty one. We'll come back after the midterm next week and talk about what happens when you actually write some data. So we'll actually write, we'll echo foo into A, and we'll see what happens. And then we'll look at what happens on a remove. Okay. I'll be in the cafe until 3:30. Labs due tomorrow night. We'll have a midterm on Monday.